Welcome to our new lecture on hyperspectral image analysis. In the context of hyperspectral image analysis, we have already talked about topics like classification and anomaly detection. In today's lecture, we are going to start with dimensionality reduction. We have already discussed before briefly why dimensionality reduction is an important problem. Let us briefly recall again. The hyperspectral images, in contrast to the multispectral images, contain hundreds of spectral bands, and this, in a way, is both advantage as well as disadvantage. The adjacent bands in the hyperspectral image are often highly correlated. The high dimensionality thus increases computational cost, and the dimensionality reduction may improve efficiency depending on exact scenario, depending on again like how much dimensionality we are reducing to. This is connected to the concept of curse of dimensionality. Large dimensions generally require more training samples, and we have already discussed how collecting large annotated data is challenging in the context of hyperspectral image analysis. With limited amount of data, classifiers may overfit, and of course there is challenges related to the interpretability as well. So with these challenges in mind, let us try to list down the potential benefits of dimensionality reduction. It includes reducing spectral redundancy, as we have mentioned that the adjacent bands, they can show high correlation. So removing some of them, reducing spectral redundancy, it can improve computational efficiency. It can enhance classification performance. On the top of this, it also improves interpretability and maybe also visualization. Here, the dimensionality reduction, this doesn't just mean like one particular path. We have at least two different paths here. One is feature selection and another is feature extraction. The feature selection, or rather band selection, this chooses important subset of the original bands. Let's say we are given 230 band originally, and let's say we are taking a subset out of this, let's say some 150 bands or 100 bands. So this is feature or band selection. On the other hand, the feature extraction rather creates new transformed features. So in this case, I will not call it band extraction. The previous one, the feature selection, I also called it as band selection, right? Whereas in this particular case, I will call it strictly feature extraction because what we are extracting is not any more bands. Selection, in a way, preserves physical interpretability because there were 230 bands and we have taken 100 bands out of it, right? So we know which are those particular bands, what is the associated wavelength, and all those details. So it preserves physical interpretability. Whereas, on the other hand, extraction often achieves stronger compactness. We need to keep in mind that the neighboring spectral bands are highly correlated. Redundant information also increases storage requirements, and thus correlation is one of the motivating factor behind this dimensionality reduction that we are trying to pursue today. Also, we can think of this as connected to the concept of intrinsic dimensionality. Even if the data, like we are presented with some 230 bands, the actual information content, this may lie on lower dimension. Now, talking about the feature selection, which we have already briefly mentioned, this selects informative spectral bands. So if we are trying to, let's say, select some 100 bands out of 230 given bands, what will we try to do? We'll try to choose these 100 bands in a way such that we retain most of the information. So we, let's say, like given a particular band, some of the other bands become redundant, right? So we will then try to remove those redundant bands. We will try to do in a way that, okay, our original physical meaning is retained. The feature selection, as we have already mentioned, is useful for more interpretable analysis. So for this, we can take the approach of band ranking. We can use some kind of statistical measures for band ranking. This band ranking can be independent of, or generally is independent of, classification models. And generally, such band ranking is based on concepts such as entropy. This is usually a computationally efficient approach. Similarly, mutual information based selection can also be pursued, where the dependency between the features and labels are computed, and higher mutual information indicates informative bands, and thus the redundant bands can be removed. We can also directly use a classifier where the approach can be like this, that feature subsets are evaluated using classifiers, and the classification accuracy then guides the selection. This, as you would have already imagined, is quite computationally expensive, as what we are talking about. Like, okay, we are taking different feature subsets and then we are again and again training some classifier. So let's say we train some CNN based classifier for now. Let's assume like that. Then we'll keep the architecture same, but we will have to train again and again with different subsets, right? So it, of course, could be like a really large number of combinations, choices of feature subsets also have. Let us imagine, okay, like we somehow restrict that feature subset, like the number of feature subsets that we are going to evaluate to a much limited number. Even then, like, okay, we are going to train the classifier for all those number of subsets. But of course, if we could do this, often this will yield strong performance. The feature extraction paradigm, on the other hand, transforms data into compact representation. The new features combine information across bands. So rather than just selecting a subset, okay, like there, of course, like 230 bands were there, and we choose 100 bands, and we said that most of the other bands are actually redundant given this 100 bands. Still, we have kind of discarded those bands, right? Even though we understand that there is a strong relationship between these discarded bands and the 100 bands that we have kept, but we are discarding them. Whereas in this case, in a way, we are not discarding any of those bands. The new features, they combine the information across different bands. It's often widely used with the classification paradigm. In this kind of approach, often principal component analysis is used. This projects data into orthogonal directions and reduces dimensionality quite efficiently. Similarly, something that I would like to mention briefly is about TSNE, which is often used in the context of visualization. This is used to project data to low dimension and then to help us visualize, to understand different properties of the data. Let us quickly go through one density-based band selection approach. Here, we'll start with a band similarity matrix, so which is L cross L matrix. So from this, of course, you can easily guess the number of original bands, right? And let's say we want to choose now out of these some key number of bands. This is what we want to choose. And let's say we have a parameter with respect to the neighborhood radius. Let's say this is some DC. In our explanation, I mean, DC doesn't play really like a strong role. You can read the original paper if you want to understand more about this DC. So what we are outputting is the selected band indices. Let's call it C. And then the cluster assignment of each band. So the 100 bands that have been selected, let's say 100 out of 230, if we go by that particular number that we have been again and again taken in this particular class. So that will be in the C, and then like A, this is the cluster assignment of each band, not just those 100. Like 100, of course, they are assigned to themselves. The remaining 130 bands as well, which are assigned to one of these 100 band. Okay, so with this background information, let us think like how to proceed. So we'll start by computing something called local density. For each band I, this quantity rho I will be computed, okay? So which you see in the exponential, and then there is a negative. And here we have, so we say that, okay, let's not think so much about the DC, but here we have the Dij, right? So Dij, you already remember from the last slide that, okay, we are talking about the particular entry from the band similarity matrix, right? So this, then we are taking a summation outside, okay? So we're doing it for rho I. So then we are taking the summation of like J1 to L and just excluding the ith term. And what can be easily seen is that high rho I implies the band is surrounded by many similar bands, whereas the low rho I value means the band is isolated. Now, with this, what we can do is we can sort these bands by this density that we have computed. So let's say we sort in descending order, and now for each band except the densest, okay, so the densest band we need not think about, but like the second densest band onwards, okay. So what we can do is we can compute this delta, this particular term, delta I, and this measures how far a band is from any denser band. So this is being computed for all the j's such that the rho j is greater than rho I, right? And for all of them we are taking the Dij, okay, Dij you remember from the similarity matrix, and there then we are taking mean out of all of those terms. So thus this indicates how far a band is from any denser band, and a large value of this will indicate that this particular band that we are talking about is actually quite far from any of the denser band, which in turn implies a potential cluster center. Now, given this, as a function of these two terms, we can compute something called band importance score. So I'm not going to the details. Again, if you're interested, you can always read the paper. Now that we have computed band importance score, we can sort the band importance score in descending order, and this will give us C, and we can also get our A, okay, such that every Aj is assigned as the argmin of Dcj. So getting like once we have this band importance score, getting the C and A both are quite straightforward. Now let us slowly start thinking about the deep learning based concepts. Till now whatever we have discussed is not in the really in the context of deep learning. Of course, the previous algorithm that we have studied, this could use deep learning in several ways, but the algorithm itself, like the way that we have studied, doesn't directly need deep learning compulsorily. So let us now start thinking about the deep learning based approaches for dimensionality reduction. We know Neural networks learn compact feature representations. Deep architectures model nonlinear structures, and the learned features then improve downstream tasks. And this is, of course, the motivation why would one like to use deep architectures, because if you think about, especially when we talk about the, like we talked about feature selection or the band selection, but also we talked about the feature transformation. And don't you think that automatically the deep networks become a good choice for feature transformation? So there, as you would have already guessed, very natural choice is autoencoders. Autoencoders consist of encoder and the decoder, where the encoder compresses spectral information, the decoder reconstructs original spectra, and the bottleneck layer, in a way, thus provides us with a reduced representation. This is widely used, that's why the dimensionality reduction. So what kind of reduction is this? This is feature transformation, not feature selection, band selection, right? Similarly, we could also adopt 1D CNN, and we can, in a way, using 1D CNN, we can like optimize both, the feature reduction as well as like some downstream classification task. And yeah, so as I have already mentioned, the compression is optimized directly for the downstream task. So this is the advantage of using the 1D CNN. Similarly, recall the case of channel attention. Channel attention we have already studied before. Given, let's say, input of dimension h cross w cross c, we will, in the first step, using some kind of pooling, let's say global average pooling, to convert it into 1 cross 1 cross c dimension. Given this, we again transform it to another 1 cross 1 cross c dimension. However, this time, this is based on some kind of learning based approach. So some learnable layers will be incorporated in between. And now this 1 cross 1 cross c, so this basically c dimensional vector, this will be used to weight the original h cross w cross c input, and we get a new modified version of this h cross w cross c. We get this output, and this now can be processed. So think like this, that what would have happened that you apply. So of course, channel attention you could apply at different stages of your network. However, what would have happened, you could just apply it, let's say, after the input, especially in the, we are talking in the our hyperspectral image analysis context, right? So if we apply the channel attention immediately after the input, in that case, what we are going to get, this in a way can work both as band reweighting. Of course, if we just retain this network, this works as a band reweighting. However, this can also work as a band selection approach. How? Like, let's say this band reweighting, this particular aspect is learned on a subset of the data, okay? And on this subset of data, you are learning this band reweighting, and then you can always check for this particular reweighting vector, and you could again, short this weighting vector and keep only those particular features or the bands which has strong weightage, and in the later, like, you got more data sets. Of course, the assumption is that the more data is coming from the similar distribution. Otherwise, probably this learned weight will not be applicable. And in small data, then you can design a slightly different network or slightly different classification paradigm where instead of applying the channel attention anymore, you already drop those bands which had got less weight previously. Think about how would one evaluate dimensionality reduction. So one is, of course, the classification accuracy after the reduction. So if, like, let's say our downstream application is like we are trying to do some classification and the accuracy drops significantly after we do dimensionality reduction, then there is no point of doing the reduction, right? Like, let's say we are doing some mineral classification and one could just say that, okay, I don't care, we just drop everything, I will keep just RGB bands, 3 channels and nothing more. I don't want those 200 bands. This leads me to like convenience for visualization and more interpretability. However, what will happen, like, given your task, mineral classification, most likely you are going to see a really strong drop in the classification. So similarly, like, of course, I took just a very extreme example. Similarly, like, even if you are just reducing from 230 bands to 100 bands, you would expect that the performance remains consistent. Similarly, one could look at reconstruction error. The visualization, of course, is an important aspect. And then computational efficiency. So now we will move to the next topic of hyperspectral unmixing. We will, for the next couple of minutes, discuss a bit of basics about this, and then we will take it forward in the next lecture. Hyperspectral pixels often contain mixture of materials, and unmixing helps us to decompose the pixels into constituent materials. The constituent spectra are called end members. So proportions are represented by abundance fractions. Why these mixed pixels? So here the spatial resolution often plays an important and limiting role. What happens is that in the case of coarser resolution, coarser spatial resolution, I mean, the multiple materials may occupy a single pixel. Application of unmixing we see in the mineral exploration, precision agriculture, urban material identification. So more or less like wherever hyperspectral images themselves are relevant, unmixing also plays an important role. So here comes the concept of end members. End members generally represent pure material spectra. So each material generally has a characteristic signature, right? And accurate end members are important for unmixing. Abundance fractions is another relevant concept. Abundances represent the material proportion. Fractions indicate basically so the contribution of each material. Abundances are estimated for each pixel, and often they will be like, we making them constrained in a way, like, let's say these are fractions, okay, like which would probably, like, of course, fraction like between 0 and 1, sum into their sums goes to 1. So these physical constraints, they like directly help us to encode the physical limits. So with this, let us stop here and we'll take forward our discussion in the next lecture. Thank you.